We're now ready to apply what we've learned about symmetry theory and point groups to a study of molecular orbitals and the quantum mechanics of molecules. Now, to illustrate this, I'm going to use a particular example. We're going to look at butadiene, which is the molecule shown here. And I'm going to focus on the carbon atom. So I haven't actually drawn the hydrogens in there, but I'm going to focus on the s orbitals and the p orbitals on the carbon atoms. Now, the butadiene belongs to the C2H point group, which is shown here, with these symmetry operations. And just to get you oriented, the plane of the molecule is a planar molecule. The plane of the molecule is the sigma H plane. All right, the very center of the molecule is its inversion center. And the C2 rotation axis goes through that inversion center and goes perpendicular to the sigma H plane. And we're going to essentially define that as the z-axis for the most part. Now, when we look at the application of group theory, symmetry theory to molecular orbitals, what we're interested in is how functions transform under the various symmetry operations. Now, I'm going to start by looking at the 2s functions. So in other words, we're going to label our various functions that are part of the basis on which we're going to evaluate the symmetry group as the 2s functions, and the subscripts are going to be the labels that identify which carbon they're on. So I'm going to number the carbons consecutively going across here. So the i's here are going to equal to 1, 2, 3, and 4. Now, if I want to create a reducible representation of how these functions are transformed underneath the symmetry or by the symmetry operations, here is in effect what I would need to do. The E operation is the easiest one, so let's just do that. Okay, the E operation operating on phi1 is going to give us phi1. If it operates on phi2, it will give us phi2, and the same thing for phi3 and phi4. Okay, so in other words, it gives us the same thing no matter what. If I were to represent this as a matrix, I might represent the matrix then as 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's basically the identity matrix. And implicitly, this is multiplying a vector of these functions. All right. Now, as we've mentioned, this is a reducible representation, but we can assign a character to it by adding up the diagonal matrix elements. So in this case, the diagonal matrix elements are 1 plus 1 plus 1 plus 1. So it will have a representation or a character of 4. Note that this only happens when the symmetry operation maps a function into itself. So by contrast, if I look at the C2 operation, I'm going to rotate this molecule around, and so I'm going to rotate C1 into C4. So in that case, my phi1 will become phi4, and my phi2 will become phi3, and so forth. None of the atoms are mapped into themselves by this symmetry operation. So that means that when I write this as a matrix, none of the elements on the diagonal of the matrix will have a number other than 0. So when I add up all those zeros, I will get a character for this particular operation. So C2 would be equal to 0. The same will be true for the character operation for I. It will also equal 0 because the inversion operation will move all of these orbital functions to a different atom, which means that the matrix that represents that symmetry operation will not have any non-zero elements on its diagonal. What about the operation for reflection? Well, again, if I have an s orbital, and the plane in which I am reflecting this s orbital is a plane that lies perpendicular to the molecule, I'm basically reflecting a sphere through this plane, so I'm going to get the sphere back. So in the case of the sigma h operation, I'm going to map phi1 into phi1, and I'm going to map phi2 into phi2. In other words, all of these orbitals will stay where they are, they will map into themselves, and they will all appear as ones along the diagonal, so the character representing the sigma h operation in this case will also be 4, just like it was for the identity operation. All right, so in this case, our reducible representation for the s orbitals will be 4, 0, 0, 4. All right, and in general, when we're doing a reducible representation for s orbitals, since they don't change sign upon any sort of transformation of the s orbital, we'll always have positive numbers there. All right, so let me write this up top here, because we're going to want to decompose this in just a moment. All right, but before I do that, I want to first look at a slightly different but related set of orbitals. Let's suppose we were looking at the p orbitals along the z direction. All right, so these are the p orbitals that are responsible for the double bonds in butadiene, and they're the ones that are going to be sticking out of the plane as we're looking at it here. So they're parallel to the C2 axis. All right, the main difference for these orbitals relative to the s orbitals is the following. When I look at their reflection in the sigma h plane, I might start with a p orbital here, and I'll draw my sigma h plane here. All right, and what I'll get out of that reflection is that the p orbitals will reflect and change sign. So in other words, the positive part of the p orbital, which started above the plane up here, will end up below the plane here when I use the sigma h reflection. So what does that mean? Well, essentially all of the work we've done here for the s orbitals would be the same for the pz orbitals, except for one. This character here will turn into a -4 when I have the p orbitals, because they flip when we use the sigma h reflection. Otherwise, C2 and I still change the atoms around, so we aren't going to have any elements on the diagonal for the pz orbitals, but we are going to end up with elements on the diagonal for the identity operator and for the sigma h operator. So in this case, the reducible representation for T2PZ will end up having the characters 4, 0, 0, and -4. All right, so you'll notice that they're different between the 2s and the 2pz, and they're different precisely because the 2pz changes sign when you reflect it through the horizontal plane, the plane that basically contains the molecule. So now when I want to decompose this into irreducible representations, I'm going to get something different when I do it for the s orbitals versus when I do it for the p orbitals. All right, so let's see what that looks like. So let's do the 2s first. Now, you'll notice that because I've got zeros for each of these symmetry operations, these are not going to affect my irreducible decomposition at all. Because what I'm doing is I'm basically taking this number times this number plus this number times this number plus this number times this number and so forth across the way. But when these are zeros, these numbers in here will never contribute to either the 2s or the 2pz decomposition. All right, for AG, what I'll end up with is 1/4, 1 over the order of the group. 4 times 1 is 4, plus 4 times 1 is 4, or 2. For BG, I'll have 4 times 1 minus 4 times 1, so that'll be 0. For AU, I'll have 4 times 1 minus 4 times 1, so that's also 0. So BG and AU will both go to 0. But you can see that BU will be the same as AG, and then it has 1s in both the E and the sigma H columns. So BU will also have a decomposition of 2. Its coefficient will be 2. So the overall reducible representation for the 2s will end up being 2AG plus 2BU. All right, what about for the 2PZ? Okay, in this case, we're going to have an opposite effect because I've got a -4 up here for the second character. It's going to eliminate when I get to these two rows, but it will reinforce when I have these two rows. In other words, I'm going to have 4 over here anyway, And AG and BU are going to have 4 minus 4 and 4 minus 4, so these will both end up being zeros. But BG and AU will end up generating 1/4 of 4 minus a negative 4, or 2, and the same will be true for AU. So my overall reducible representation will end up decomposing as 2BG plus 2AU. All right, and we'll see that the s orbitals generate different irreducible representations than the pz orbitals, and it all has to do with the sign of the operation, the symmetry operation through the plane of the molecule. All right, one last note, and that is, in each case, we started off with a set of 4 atomic orbitals. So what we should get out of this are 4 linear combinations that will generate molecular orbitals, or symmetry-adapted orbitals. All right, and that's exactly what we've done. 2 of those, in the case of the 2s, 2 of those will have the irreducible representation of AG, and 2 of them will have the irreducible representation of BU. But there is a total of 4 that are generated. The same is true for 2pz. We generate 4 irreducible representations, so 4 different ways that we combine the pz orbitals in order to create symmetry-adapted orbitals in the C2H point group.